In this video, we will talk a little bit about restoring forces. For some materials, if you deform them, they will not return themselves to their original shape. For example, clay, dough, things like that. If you deform them, they maintain their new shape or something not like their original shape. Other materials, if you deform them and then release them, they restore themselves to their original shape. For example, sponges, a volleyball, spring, stretchy band. In this video, we are specifically talking about the physics of the objects that do restore themselves to their original shape. In this PHYS simulation, we can see that if I put a cylinder on this spring, the force of gravity pulls it downward and accelerates the cylinder downward. But as it does, it deforms the spring that it's attached to, which exerts a force that starts out at 0 newtons but increases in magnitude the more the spring stretches. Here we see that the force of the spring equals the force of gravity in magnitude, and the cylinder is held stationary. When the relationship between the change in length of the spring and the restoring force of the spring is a direct relationship, that is known as Hooke's law. That is the same Robert Hooke who discovered that under a microscope, cork has a structure that looks like monastery cells. This relationship takes on many forms, and we care about it right now in one dimension. A couple of pointers about springs and other objects that follow Hooke's law. 1. The phrase ideal spring means that the restoring force is proportional to the amount of distance that the spring has been stretched or compressed. The more you distort the material, the harder it pulls itself back to its original shape. 2. The spring has some length before distortion where the net force on it is 0. Pay attention to the wording of the question to be clear on how long that spring length is when there's no force applied to it. And 3. Note that if I stretch a spring to the right, the restoring force points to the left. By definition, that's what it means to be a restoring force. Thus, mathematically, Hooke's law has a negative sign built in. Please do not let this negative sign throw off your calculations. The negative sign expresses that whatever physical distortion has been done to the spring to stretch it or compress it, the spring is exerting a force in the opposite direction in an attempt to restore itself to the original shape. And one other note, an ideal spring can be stretched or compressed. Make sure you know what's happening in an individual problem. Drawing a picture of the problem makes it a lot easier to be sure of what exactly is happening, so please do this. For example, this question says, suppose a spring stands vertically on the table. Its length is 10 centimeters, and a 7.2 kilogram box is balanced upon the spring, compressing the spring to a new length of 8.92 centimeters. The drawing makes it really clear what exactly is happening, and the change in spring length for this calculation would be the difference between the original length of 10 centimeters and the new length of 8.92 centimeters. I do want to note that if you stretch a spring too much, you can permanently distort or even break it. We will not be talking about that phenomena in this course, other than to note that right here, Hooke's law is a real relationship, but not all stretchy things follow it. The physics of materials restoring their shapes can get really complicated. We want to talk about the linear relationship that occurs in an ideal spring and other materials that are similar to an ideal spring. I would like to explain to you an experiment that I've done. I want to show how I can experimentally determine the spring constant of this particular spring that's in this picture on the left side of the screen. The spring constant is a value that tells us something about the stiffness of a particular spring. It relates how much force is needed to stretch or compress a spring from its natural length to some new length. This is my setup. I attached my spring to the force sensor, as you can see here, and I grabbed the force sensor and I pulled it to the right on our screen to stretch the spring out, while the force sensor was recording the amount of force that the spring is exerting back in the other direction as the spring attempts to restore itself to its original shape. I set up a graph for my data. The graph looks like this before I started recording. Force on the vertical axis and position on the horizontal axis. Please note that the graph is not always shown this way. The axes are sometimes reversed. I prefer showing it this way because in this way, the slope of my graph will be the spring constant. So here's the setup. I stretch the spring, then I bring it back. The motion detector is on the right to measure how much I've moved the cart. The card is only here to make it easier for me to get a smooth movement, a smooth measurement as I stretch the spring. How far the cart moves is however far the spring stretches. And this is the graph that I got. This is my data. We see a linear relationship between the distance I have stretched the spring and the force the spring exerts to pull itself back to its original shape. This graph is giving us a linear slope, a linear relationship between the spring force versus the distance stretched, just exactly as Hooke's law predicts. We care about how steep this slope is. The steepness, the value of the slope, is the spring constant, which is the symbol K in Hooke's law, and the units will be in newtons per meter or newtons per centimeter. Studying Hooke's law is useful for understanding springs and other elastic materials, but it is especially useful in laying the foundation for a topic we will get into a little bit later in this course. That topic is simple harmonic motion, which helps us model things like the interactions of atoms in a solid structure. The bonds between atoms can be modeled as springs in a lot of cases. Okay, that's it for this video. I'd like to do some examples where you can see how Hooke's law is actually utilized.